I hope you weren't listening to this in your phone with earbuds. That could have really hurt your ears, and I would hate for that to happen. We've been learning about trig functions of angles within right triangles. Now we're going to expand our horizons and look at angles within the context of the coordinate plane. X-axis, y-axis, and if we've got an angle in standard position, initial side along the positive end of the x-axis, terminal side shooting off. And let's say all we know is a single point on this angle. And let's say that point is 12,5. I traveled 5 units right, 12 units right, and 5 units up. Okay. Where my angle intersects the circle, I can drop a perpendicular, creating a right triangle.
Haven't we been working with right triangles already, Mr. Simmons?
Yes, we have. Quite a bit. So you should remember quite a lot about right triangles. Now, what would the length of this leg be?
I'm going to guess 5.
And you would be wrong.
Oh my gosh!
X coordinate, Y coordinate. Go over X units, up Y units. So that length is 12.
12.
And this length,
5.
5. But what about the hypotenuse here, which is also the radius of this circle? What would that length be?
If I had to make a guess, I would think we could use the Pythagorean theorem to determine
I
that.
think you are right. So, over here, leg squared plus leg squared equals hypotenuse squared. What do you see? 25 plus 144 equals c squared. That adds to 169. And I take the square root of each side, and I'm only interested in the principal root. And the square root of 169 is 13. Now,
That looks a little familiar, Mr. Simmons.
we started with just an angle, not a triangle, just an angle. And so that's the angle I'm interested in,
That's theta,
theta.
like the cheese. Theta? Oh, no, it's T-H-E-T-A. Yeah, it's theta.
All right. Okay. So we're on the sine, our good friends, the 3 trig functions and their cousins.
They're first cousins, that's right.
Sine of cousins. I mean, sine of theta.
It's going to be a great video.
Opposite over hypotenuse. Opposite over hypotenuse. 5/13. Cosine. Adjacent over hypotenuse. 12/13. Tangent. Opposite over adjacent. 5/12. And their cousins are just the reciprocals. You've got 13/5, 13/12, and 12/5. Okay.
Very nice.
But if we generalize this,
Generalize.
go from the specific to the general, a pattern, a formula, if you will, that can be applied to any situation.
Would you like for me to do that, Mr.
Please.
Simmons? We'll swap since I'm right-handed. Alright, so cool. Alright, so we go from the specific to the general. I'm going to swap colors here just a little bit, maybe use a darker color. Alright,
Use a dark
the distance that we traveled here was 12 units along the
X-axis.
x-axis. So we're going to call this our x length. The distance that we traveled here vertically is not necessarily along the axis, but it is vertical. So that must be the y value. So we'll let phi be y, as shown here in our ordered pair x, y.
Y.
Alright. And we said that the length from the center of the circle out to the circumference, or out to the circle, is the radius. We'll call that r. So the relationship here is x, y, and r. So generally speaking, 5 is my y value. And then 13 is the radius, so that's y over r. And then 12 is my x value over r. And then 5 is my y value over my x value. And then, of course, we have the first cousins, which are reciprocals. So that's r over y, and then r over x, and then x over y. So what we see here is we can generalize all of these values and not just have 5, 12, 13. We could have any point along the circumference of this circle. So I'm just curious, Mr. Simmons, what if we were to choose a point over in, say, the third quadrant? How would that affect things? So why don't we start here, and let's wrap this all the way around to a point, and I'm going to just use this point here along the terminal side of this angle.
All right.
Now, would you like to just call this negative 12, negative 5, perhaps?
Sure.
Or would you like to use something different?
Let's go a bit. Yeah, we could do that.
Okay.
Yeah, that's pretty much a straight line.
All right, we'll call it negative 5, negative 12, right? Now, if we're going to do this, here's this angle. You recall the angle in quadrant 1 is acute, meaning it's less than 90. But obviously, this angle that we created here is greater than 180 degrees.
Correct.
Or something like pi radians, I would assume. So that can't be a triangle. What are we going to do to make this thing a triangle? All this is based off a right triangle trig, Mr. Simmons.
Right. Well, we can fold our paper up this way and that way, and that could give us a triangle.
But this isn't paper.
Oh, well,
Dadgummit.
what if we just draw a line right to the x-axis?
Ah, let's do that. So we just kind of do a vertical leg right here.
Sounds good.
So now instead of this whole angle that we have here, this theta, this new theta, we have an angle here that gets closest to the x-axis from our terminal side.
Similar to a reference angle.
It's a reference angle. That's exactly what it is. And why don't we call this reference angle? And I'm going to change colors here a bit. Purple, I don't know how well you can see it on the video. But this is our angle. Why don't we call this alpha? Instead of theta, we'll call it alpha. This is our angle, and if you'll notice, we have our triangle here. Negative 12, negative 5 would be the coordinate on the circle.
Correct.
That's where this triangle here is touching the circle. So if we use these values, we can plug them into the same place that we plugged here. So let's go back. Oh wait, we got to make sure we have all our sides. So that is a length of 5, right? Now obviously we're going negative, but this is a distance. This is a length, not 5 but 12. I apologize about that, guys. So it's 12. So this is 12, and then this length here would be 5, and of course the length of the hypotenuse is going to be 13. So when we go back here, let's look at this. So we've got 5 over 13. Nothing really changed right there, did it, Mr. Simmons?
Well, I don't know. It says y, and the y coordinate here is negative.
Oh my gosh.
Because we started the origin and we moved down.
So it's got to be a negative 5, guys. So we've got to go over here and change this then to a negative 5 13ths. So it's a negative ratio. And then if we go over here to the cosine, it's 12 13ths. Did anything really?
I think it changed as well.
Negative 12 over 13. Okay, now what about tangent, Mr. Simmons?
Well, they both changed. Y over x, negative 5 over negative 12. But a negative divided by negative,
It's a positive.
it's a positive.
So we can just leave that as 5 12.
Sure.
Because
Yeah, it's still positive.
it's still positive. Now 13 fifths. If we go up here and look at this reciprocal, this is really a negative 5.
Correct.
But we don't usually have a negative in the denominator of a fraction.
No.
We either put it off to the side,
Right.
by the bar, the vinculum, if you will.
Or we stick it in the numerator.
Or we stick it in the numerator. So I'm going to just move that up and leave it in the numerator. Then we have 13 twelfths, again reciprocal. Negative really doesn't hang out in the numerator, the denominator. So I'm going to put it in the numerator. And then of course the 5/12 become 12/5. And obviously, again, positive, negative divided by negative is going to be a positive, so we're going to leave that alone there. So what have we noticed here? Given a point somewhere on this circle, we can use our right triangle trig and what we know about angles and reference angles
in order to come up with all 6 trig functions. And all we really needed was 1 point on the terminal side of the angle
1 point on the terminal side of the angle
to get all 6 trig functions.
All 6 trig functions. Is there anything else we need to do, Mr. Simmons, or would you like to call it on this video?
Let's call it.
You guys are going to enjoy this short video. We're out of here.